Let's consider a differentiable function f on a closed interval a to b. If we draw the secant line between the two endpoints, then the slope of the curve has to somewhere match the slope of the secant line. In other words, there must exist some input c such that f prime of c is equal to f of b minus f of a over b minus a. This is the statement of the mean value theorem. And it doesn't really seem like anything too surprising or impressive. It's a very plausible statement geometrically. Nevertheless, it'll play a critical role in a bunch of important proofs going forward. We'll use it to prove all sorts of results related to differentiation, and ultimately we'll use it to prove the fundamental theorem of calculus. And our proof of this statement will be relatively brief, but that's a testament to all the machinery regarding limits, continuity, and differentiability that we've already established. Let's start with a simpler version. So let's modify this picture so that the heights of the endpoints must be the same. F of a must equal f of b. In that case, our slope expression, f of b minus f of a over b minus a, would simplify to 0. So our conclusion is that there's some input c between a and b whose derivative is 0. We can first prove this simpler version, and then that'll help us prove the full version. This is called Rolle's theorem. Let's write out this statement. Let f from the closed interval a to b to r be continuous on the closed interval a to b and differentiable on the open interval a to b. If f of a equals f of b, then there exists some input c in the open interval a to b such that f prime of c equals 0. For the proof, we'll start by citing the extreme value theorem to say that because f is continuous on a compact domain, f achieves both a maximum and a minimum. Now we'll be able to use our interior extremum theorem from last video. That was the theorem that's silently used in optimization problems to say that if f has a max or a min at some point, then its derivative there is 0. The reason we can't immediately apply this result is because we'd need the max or min to occur in the open interval a to b. So let's first consider the case where both the maximum and minimum occur at the endpoints. Since f of a equals f of b, the only option for f is to be a constant function at this height, in which case f prime of x is 0 on the whole interval. And so we can choose c to be any point we want. And then if this is not the case, then either the maximum or minimum occurs at some point in the open interval a to b. We can let c represent this input and note that by the interior extremum theorem, f prime of c equals 0, proving Rolle's theorem. Let's state and prove the full mean value theorem. If f from the closed interval ab to r is continuous on the closed interval a to b and differentiable on the open interval a to b, then there exists a c in the open interval a to b such that f prime of c equals f of b minus f of a over b minus a. So the hypotheses are very similar, but we don't have that f of b equals f of a. Let's look at our mean value theorem picture again. And we want to define some new function, say g, such that g of a equals g of b, that would allow us to use Rolle's theorem on g and then backtrack and get some sort of conclusion about f. Maybe pause the video for a moment and think graphically about how we should define this g of x. I want to let g of x represent the distance, the vertical distance between our secant line and our curve. In this way, g of a and g of b would both be 0. And then when I use Rolle's theorem to conclude that there's some input such that g has a derivative of 0, that'll correspond graphically to when this distance is unchanging, which should also correspond to the same spot where the derivative of f matches the slope of the secant line. So let's write this down in a proof. Let m equal f of b minus f of a over b minus a. So m is representing the slope of our secant line. Define g of x to equal f of x minus f of a plus m times x minus a. We're subtracting off the equation of the secant line. Now let's verify that the hypotheses of Rolle's theorem hold. G is continuous on the closed interval a to b and differentiable on the open interval a to b by, say, the algebraic continuity theorem and the algebraic differentiability theorem, because it's just a combination of functions that already have this quality. And then for the second hypothesis, let's verify that those endpoints are equal. Compute g of a equals f of a minus f of a plus m times a minus a equals 0, and g of b equals f of b minus f of a plus m times b minus a equals f of b minus f of a minus m times b minus a, which equals 0 by the definition of m. So, by Rolle's theorem, there exists C in the open interval a to b such that g prime of c equals 0. Now we just want to conclude that f prime of c equals m. Differentiating the definition of our function g, we get that g prime of x equals f prime of x minus m. Evaluating at x equals c, f prime of c minus m equals 0, which implies that f prime of c equals m, proving the mean value theorem. Let's see an example that demonstrates how this mean value theorem can be used to prove other things. It's pretty straightforward to show from the definition of the derivative that any constant function has a derivative of 0 everywhere. But this is an if and only if. If f from I to r is differentiable on an interval I, and f prime of x equals 0 for all x and I, then f of x equals k for some k in the reals. For the proof, let a and b be in the interval I with a strictly less than b. Then, by the mean value theorem, there exists c in the open interval a to b such that f prime of c equals f of b minus f of a over b minus a. But we know f prime of c has to be 0, and so 0 equals this quotient, which implies that that numerator, f of b minus f of a, equals 0, so f of b equals f of a. And because a and b were chosen arbitrarily, the same argument works for any pair of points, so f is a constant function. We could further prove, say, that if f and g are differentiable functions on an interval I that satisfy f prime of x equals g prime of x for all x and I, then f of x equals g of x plus k for some constant k in R. So if two functions have the same derivative, then they must just differ by a constant. Using that previous result, the proof is very brief. Let h of x equal the difference function f of x minus g of x. Note that h prime of x equals f prime of x minus g prime of x equals 0. Apply our previous result to conclude that h of x equals k, and then add g of x to both sides. Now I said we'll be able to prove a bunch of derivative rules from the mean value theorem, and that is true, but a lot of them need a slightly stronger version. Let's state the generalized mean value theorem. Let f and g from the closed interval ab to r be continuous on that closed interval and differentiable on the open interval a to b. Then there exists a c in the open interval a to b such that f of b minus f of a times g prime at c equals g of b minus g of a times f prime at c. And it's stated this way so that it still holds when g prime of c is equal to 0. But if we assume that g prime of c is not equal to 0 and g of b is not equal to g of a, then we could restate the conclusion as f prime of c over g prime of c equals f of b minus f of a over g of b minus g of a. These ratios must be the same. Our proof will not depend on this picture, but just to build visual intuition for this statement, it's best to imagine a parametrized path through the xy plane determined by the two functions x equals g of t and y equals f of t. Then we can draw this curve starting at, say, some time t equals a, ending at some time, say, t equals b, and we can examine the straight line connecting these two endpoints. Its slope is f of b minus f of a divided by g of b minus g of a. And on the other hand, the slope of the tangent to the curve at any moment t is given by f prime of t divided by g prime of t. And by that same geometric intuition we used before, there has to be some input where the slope of the tangent to the curve matches the slope of the secant line. And so in these terms, that would be a value of c such that f prime of c over g prime of c is equal to f of b minus f of a over g of b minus g of a. Let's turn our attention to the proof. Again, we'll define an auxiliary function to which we can apply Rolle's theorem, and then backtrack to make conclusions about the derivatives of the original function. Let h of x equal f of b minus f of a times g of x minus g of b minus g of a times f of x. We'll note that this new function h inherits the quality of being continuous on the closed interval a to b and differentiable on the open interval a to b from f and g because it's a linear combination of them. Computing the endpoint values, h of a equals f of b minus f of a times g of a minus g of b minus g of a times f of a, and h of b equals f of b minus f of a times g of b minus g of b minus g of a times f of b. We can factor the difference h of b minus h of a as f of b minus f of a, g of b minus g of a, minus g of b minus g of a, f of b minus f of a, and this equals 0. So h of a equals h of b. Now, by Rolle's theorem, there exists c in the open interval a to b such that h prime of c equals 0. Now, just like how we proved the ordinary mean value theorem, we'll differentiate our helper function and evaluate at c. H prime of x equals f of b minus f of a g prime of x minus g of b minus g of a f prime of x. Evaluating both sides at x equals c, f of b minus f of a times g prime of c minus g of b minus g of a times f prime of c equals 0, and thus f of b minus f of a g prime of c equals g of b minus g of a f prime of c, proving this generalized mean value theorem. As a first application of this generalized theorem, let's prove L'Hopital's rule from a Calc 1 course. So stated formally, let f and g be differentiable on an open interval I containing a, except possibly at a. Assume that the limit as x approaches a of f of x equals 0, and the limit as x approaches a of g of x equals 0. If g prime of x is not equal to 0 for all x not equal to a, then the limit as x approaches a of f prime of x over g prime of x equaling L implies that the limit as x approaches a of f of x over g of x equals L. And this justifies, under certain conditions, taking the derivative of a numerator and denominator and preserving the value of a limit. We'll refer to this first statement as the 0 over 0 form to distinguish from the infinity over infinity form that'll be the second half of L'Hopital's rule. Since we required that the limit as x approaches a of f of x or g of x was equal to 0, we can redefine f of a and g of a to equal 0 without affecting this limit. Let xn be a sequence convergent to a such that xn is greater than a for each n. We can apply the generalized mean value theorem to f and g on the interval a to xn. For each n, there exists some cn in the open interval a to xn, such that f of xn minus f of a over g of xn minus g of a equals f prime of cn over g prime of cn. And it's legit to write this form, because we know both of those denominators are non-zero. The denominator on the right is non-zero just by the given condition that g prime of x is not equal to 0 for all x not equal to a, and the fact that cn is not equal to a. But the reason that the denominator on the left is non-zero is a little more subtle. That denominator is just going to become g of xn, since we've defined g of a to be 0. And since g is a differentiable function with a non-zero derivative everywhere except for a, it has to be monotone, either strictly increasing or strictly decreasing, on the portion of the interval I greater than a. And since g of a is 0, that means that g of x is non-zero for all x greater than a. Since f of a and g of a are 0, we can rewrite this as f of xn over g of xn equals f prime of cn over g prime of cn. Since xn as a sequence converges to a, by the squeeze theorem, the sequence cn also converges to a. We assumed that the limit as x approaches a of f prime of x over g prime of x was equal to some L. And so taking the limit of both of these sequences, the right-hand side, f prime of Cn, g prime of Cn, will be replaced with L, which will be equal to the left-hand side, which is the limit of the sequence f of xn over g of xn. And recall that xn was an arbitrary sequence of terms strictly greater than a converging to a, but we could do a similar argument for an arbitrary sequence of terms xn less than a converging to a. And so this limit exists and equals L. The limit as x approaches a of f of x over g of x equals L. If we replace the hypothesis that the numerator and denominator tend towards 0 with the hypothesis that the numerator and denominator tend toward infinity, the claim still holds. We briefly discussed limits equaling infinity, but let's write down that definition. Given a function f from a to r and a limit point c of a, we say that the limit x approaches c of f of x equals infinity if, for every real number m, there exists a delta greater than 0, such that for all x with 0 less than the absolute value of x minus c less than delta, we have that f of x is greater than or equal to m. So this infinite limit definition replaces our epsilon window that we're required to be within with a real number threshold that we're required to be above. Now, stating the infinity over infinity form of L'Hopital's rule, assume f and g are differentiable on the open interval a to b, and that g prime of x is not equal to 0 for all x in the open interval a to b. If the limit as x approaches a, g of x, equals infinity, then the limit as x approaches a of f prime of x over g prime of x equaling L implies that the limit as x approaches a of f of x over g of x equals L. And this would just be the right-handed half of the infinity over infinity form of L'Hopital's rule. If you replaced a with b in these limit expressions so that the input would instead be approached from the left, the result would still hold. And also, if you replaced the infinity over infinity with a negative infinity over negative infinity, the result would still hold. And we could prove this like we did in the last example, using a sequential characterization of limits, or we could use the epsilon delta definition. So let's use that second route. Let epsilon be greater than 0. Since the limit as x approaches a of f prime of x over g prime of x equals L, there exists some delta 1 greater than 0, such that the absolute value of f prime of x over g prime of x minus L is less than epsilon over 2 for all x strictly between a and a plus delta 1. Let's let t equal a plus delta 1, representing the right endpoint of this first half delta window. Our function isn't defined at a, and so we can't apply the generalized mean value theorem to the interval from a to t. But for any x greater than a, applying the generalized mean value theorem to the interval x to t gives us that f of x minus f of t over g of x minus g of t is f prime of c over g prime of c for some c in the open interval from x to t, so long as g of x is not equal to g of t. We've assumed that g prime of c is non-zero, so we're not concerned about that right denominator. Since t is fixed and the limit as x approaches a of g of x equals infinity, we can choose delta 2 greater than 0 such that g of x is greater than g of t for all a less than x less than a plus delta 2. And this comes directly from the definition of the infinite limit. Now, you might be concerned about the strict inequality, because in the statement of that definition we put greater than or equal to m, but you could just take your m to be g of t plus 1, in which case we get the strict inequality for g of t. And that definition would be equivalent if the inequality with m was strict. And this statement does two things. It guarantees that denominator is non-zero, but it'll also allow us to isolate f of x over g of x with some algebra. Our choice of t implies that the quotient f of x minus f of t over g of x minus g of t is in the epsilon over 2 window around L, because that quotient, by the generalized mean value theorem, was equal to f prime of c over g prime of c for some c in the interval x to t, which is a subset of a to t. And instead of using our epsilon window capital V notation, I've just written this out as a string of inequalities so that we can think about it more algebraically. For all x in the open interval a to a plus delta 2, that smaller window where both of these desired conditions hold, we can multiply all three sides of this inequality by g of x minus g of t over g of x, in attempt to cancel out that current denominator and replace it with a g of x. And our assumption that g of x is greater than g of t guarantees that this is positive, so it doesn't reverse the direction of the inequality. We can simplify that expression to 1 minus g of t over g of x on the left and right-hand side, and simplify the middle to f of x minus f of t over g of x. Expanding the left side and right side algebraically and adding f of t over g of x to all three sides, we get just f of x over g of x in the middle as desired, and we get these two nasty expressions on the left and right. But those extra terms are things that we can bound. Since t is fixed, and the limit as x approaches a of g of x is infinity, we can choose a delta 3, such that for all x in the open interval from a to a plus delta 3, g of x is large enough such that both of these expressions are less than epsilon over 2 in absolute value. Letting delta represent the minimum of delta 1, delta 2, and delta 3, combining all of this together for any x in the open interval a to a plus delta, the absolute value of f of x over g of x minus L is less than epsilon, completing the proof. In the next video, we'll discuss the relationship between differentiation and inverse functions, and then we'll look at the construction of a continuous, nowhere differentiable function.